Today give our colloquium. So Thomas Schäfer is the Wesley O'Doggett Distinguished Professor of Physics at North Carolina State University. He received his PhD from the University of Regensburg in 1992, and he joined the faculty of North Carolina State University in 2003, and he was promoted to full professor in 2006. He received a Theodor Linen Fellowship from the von Humboldt Foundation in 1992, an Outstanding Junior Investigator Award from the DOE in 2002, and was elected Fellow of the APS in 2006. He also served as a member of the National Academy Study for the US-based Electron-Ion Collider Science, and also as a member of NSAC, the Nuclear Science Advisory Committee. He is an expert on QCD, many body effects in atomic, nuclear, and particle physics, and also transport theory. And today he will be talking about the beam energy scan theory collaboration and the results that the collaboration produced in the last few years. Go ahead, Thomas. Welcome.
Well, thank you so much for having me. So it's 9 o'clock in the morning in Raleigh, North Carolina. It's actually still pretty cold outside, but it's very spring-like, so the sun is up. So thanks a lot for the invitation to give a talk about the beam energy scan theory collaboration. I don't think I have to explain to this audience what the goals of that collaboration were. The goals of the collaboration were to provide support for the experimental program at Brookhaven. And that program, of course, is somehow centered on two questions. First, whether we can somehow locate the QCD phase transition, either by seeing a critical point or by maybe identifying a first order phase transition, and whether we can identify anomalous transport phenomena that are specific to a quark-gluon plasma. And so there were obviously some intriguing hints after the first stage of the beam energy scan. And what the BES collaboration really is trying to do is provide a set of theoretical tools to analyze the data that everybody's eager to see. So it was a 5-year DOE-funded effort. That effort is now sort of formally over. Doesn't mean that we're not working on it anymore, but the money's gone, and we actually briefly put out a report that kind of summarizes the effort of the past 5 years. So this is the paper which you can read in Nuclear Physics A, and on the archive, you also see the set of authors that have contributed to it. That includes in particular the co-PIs of the effort. That was Swagato Mukherjee at Brookhaven and Volker Koch at Berkeley. The collaboration also provided a set of software tools, and those two are for the most part open access. And here's a link where you can see, or you can find and obtain some of these tools. So this is an outline of the report that we put on the archive. Contains a number of subjects, starting from Lattice QCD, some general thoughts on critical fluctuations, looking at an equation of state that has an Ising critical point, and then a variety of kind of hydrodynamical tools. So initial conditions, hydrodynamic tools for the lower beam energies, critical and non-critical fluctuations, freezing it out, and a global modeling framework. So that's obviously a lot of material. So for the purposes of this talk, I decided to not cover all of this. So this is a kind of reduced outline, which I thought was material that I could reasonably cover in a talk like this one. So in particular, all the material on anomalous transports and the isobar run and so on. So that I consider somewhat separate, and I will not talk about it today. And I will also not go into great detail regarding our analysis of backgrounds. So that all of that you can read about in the report. Okay. So let's start with the lattice. So these are a number of slides that I took from the report. The observables you've probably seen many times, but there are a number of important updates contained in the work. So the plot you see on the left is the curvature of the crossover transition here done for so-called kind of realistic values of the strangeness and quark number. So we take the quark number to be 40% of the baryon number, and you see the curvature of the freeze out curve. So this is this very small curvature that's also been seen in other lattice calculations. The plot you see on the right is an attempt to see whether there is any kind of sharpening of that crossover transition as you go out in the chemical potential direction. That is obviously what you would expect to see if you're somehow coming close to a critical point. And so this is a plot of the susceptibility at different values of the baryon chemical potential. And what you can see is that at least in the regime that can be studied, you don't see any evidence that the shape is changing. And this is also the plot here. So this is a measure of this width. So this blue band is about 15 MeV. So this is the 15 MeV width. And you see that there's no obvious evidence that that is sharpening. Of course, eventually the error bars are increasing. So it could be sharpening around 300 MeV, but in the regime where you can do this accurately, there's no evidence that it does. A set of observables is obviously very important for a lot of the things we do are these baryon number cumulants or the associated susceptibility. So this is a set of calculations, again, for these conditions where we take the electric charge to be 40% of the baryon number. So the second, the fourth, and the sixth baryon number cumulants. So formally, these are just derivatives of the pressure with respect to the chemical potential. They can be computed for all the conserved charges, so B, Q, and S. And these particular results are just strictly at zero chemical potential. So that can be obtained, obviously, either by computing the observables directly or by computing it for imaginary chemical potential and then Taylor expanding. And these are the Taylor coefficients. So this is a set of results that we will use in just a little bit to constrain the equation of state as we take it out into the chemical potential plane. What was also done is that you can take these cumulants and again, take them into the chemical potential plane. So again, that can be done by a variety of methods, either by computing even higher cumulants that constrains the chemical potential dependence of the lower cumulants, or again, by doing the low order cumulants and doing it at imaginary chemical potential. So here, this is a somewhat busy plot and also a somewhat ambitious effort, because in this particular plot, this is now being overlaid by actual data. Obviously, there's a model that went into this to determine how we should map the actual data, the beam energy of the actual data, onto the baryon chemical potential. So that was the standard kind of freeze-out thermodynamics that was done by Peter Braun-Munzinger and collaborators. So you see that, and this is here done for two different possible freeze-out temperatures. So you see that there actually is quite some sensitivity as to what you assume. But you see that the lattice data shows some indication that this ratio of the fourth to the second order cumulant is somewhat dropping with baryon chemical potential. And the same kind of indication is seen in the data. Now, obviously, there is some uncertainty that, if the freeze-out temperature is changing as you change the baryon chemical potential, it's not quite as obvious that there should be an effect. So what is ultimately probably the better way to do this, and there are analogous plots in the report, is to do it completely from cumulant ratio. So instead of trying to take a freeze-out chemical potential and plot it against a cumulant, to just plot one cumulant against another. So for example, to plot the ratio of the fourth to second over the third to first. And that actually shows similar indications that you would expect that ratio to drop as you lower the beam energy. Now, ultimately, the idea was, of course, that, or the simplest version of the idea is that an observable like this one would eventually show non-monotonic variation. And indeed, there's a little bit of a hint of that in the BES-I data, that you would initially see this kind of drop, and then eventually it would change sign, and that would be an indication of a critical point. And that could, of course, be the case. It could be that when the data is taken, there's a very, very clear indication of this, and then maybe not all that much theory is truly required to make an announcement of a discovery. Now, but in reality, that may not be the case. So things may be more complicated in a variety of ways. So number one, it probably is the case that if this is observed, this will always be in a regime that cannot easily be accessed by lattice, at least not with the methods that are available now. So we may have to do some modeling on the equation of state. And in addition to that, of course, all of these comparisons of lattice cumulants to data they always assume that you're in thermal equilibrium at freeze out so that you can directly just map one onto the other. But there are, of course, many indications that non-equilibrium effects are important, that freeze-out effects are important, that resonances are important, that charge conservation is important, and so on. And so it's this kind of observation that really motivates the kind of non-lattice part of the BEST effort. And so this is what I will be talking about in the rest of this presentation. Okay. So before I do that, just a few sort of small reminders about fluctuations. So we think that if a critical endpoint does indeed exist in the QCD phase diagram, that ultimately this is just an endpoint of the usual easing variety, meaning that this endpoint, at least in terms of its symmetries, is exactly the same as the endpoint of the liquid-gas transition in ordinary water. Okay. So then you have an easing-like order parameter, which here I just generically call psi. So for QCD, we often think of this in terms of the entropy per particle, but there are many scalar order parameters that in principle you could use. Okay. So I can then construct a functional that governs the probability of a fluctuation to occur. And here I write a fluctuation of the order parameter and the energy density of the system. And that probability is ultimately just governed by some kind of entropy functional. Okay, so it's an entropy functional that depends on an order parameter, which could be a magnetization or entropy per particle or something like that, and an energy density. And as soon as you have an entropy functional like this, you can always construct just the corresponding conjugate variables. And in the easing model, so here are the original densities, which I denote by little x. This, by the way, is just Landau's notation. And the corresponding conjugate variables, I just denote by a capital X. And in the easing model, the conjugate variable to energy density is a reduced temperature, and the conjugate variable to the order parameter is a magnetization. And of course, we think that in QCD, there is a corresponding conjugate pair. So in QCD, we have two densities, which you can take to be the energy density and the particle density, and two conjugate variables, which you can take to be the inverse temperature and the chemical potential. And when we say that QCD is easing-like, really what we're saying is that there's a map from these variables in QCD to the easing variables, and that there's an associated map from these variables, temperature and chemical potential, to the easing variables, which are reduced temperature and magnetization. And so here, very schematically, you see what this looks like. So in the easing model, so this is the plot that we always show when we teach statistical mechanics. So there's a first order phase transition, and there's an endpoint, the Curie point. And you can go from one side to the phase transition to the other by just applying a magnetic field. And this is the direction of the reduced temperature. And so what we're saying is that there's some kind of map from this easing system to QCD, where this is maybe a slightly funny way to plot the QCD variable. So there's reduced temperature, there's inverse temperature and chemical potential, and there's a possible first order phase transition with an endpoint. And of course, if you plot this instead in terms of the densities, then this first order phase transition really has a coexistence regime. So in the easing case, this is a coexistence regime in terms of the order parameter, and in the QCD case, this is some coexistence regime in terms of energy density and particle density. And what the slide says is that simply as soon as you decide on some kind of map, all of these other relations are now implied. They just follow from thermodynamic identities. Okay. So we applied this kind of idea to constructing an equation of state for QCD that has a possible critical endpoint in the universality class of the easing model.
Thomas, there is a question from Bernd Müller. Bernd, do you want to ask your question directly?
Yeah, Thomas, very nice introduction so far. When you say there is a map between the EC model and the QCD that maps the variables on one side to the variables on the other side, what exactly does it mean there is a map? Does it mean a map that leaves the entropy functional invariant, or what exactly does it mean?
Well, we do that kind of exercise all the time. So there are obviously, for example, many fluids that have a first order phase transition in the easing universality class. But these phase transitions occur at different physical temperatures, and the jumps in density are different jumps, and the precise shape of the first order regime is not an exact parabola. But all of these, by universality, you can apply a map to the temperature pressure regime, and just map them onto a universal curve. And then the claim of universality is that the non-analytic part of the equation of state is universal when you do that, when you map them to the correct variables, so that you can superimpose on your physical pressure and temperature variables a map that maps it onto the Ising model. So that's when we show this kind of data collapse in the standard StatMech textbook. That's what we're doing. And what we're trying to do here is the same for QCD, that we're saying the QCD pressure has a regular contribution, which has nothing to do with the Ising model. And it has a critical contribution. The critical contribution is still a function of temperature and baryon chemical potential. We claim that critical contribution is just the Ising pressure when written in suitable variables. And the only thing one has to remember is that that map doesn't have to be rectilinear. It's, you know, the two axes, T and mu, are kind of orthogonal, but they're mapping onto reduced temperature and magnetization does not have to be conformal. It can distort the angles.
Okay, but so basically what you say is that there should be an analytical map of the non-analytical part of the thermodynamic variables.
Yes.
Okay, thank you.
And that is indeed what one does for ordinary fluids. And it's our attempt to do this here. So again, the idea is to just split the pressure into a regular contribution and a critical contribution. That critical contribution is just taken to be the Ising equation of state. There's many years of work on that. There's a standard parameterization that you can find just by opening Saint-Justin's book. And then again, in general, that can be a complicated map, but at least locally, indeed, you can just take it to be a linear map. But we're allowing the axes of the two temperature planes to have some angle with regard to one another. And we're allowing the reduced temperature and magnetization to not be orthogonal, so that there are two different angles that occur in this mapping. And then the way we constrain this equation of state is that we demand that when we take this whole functional and we re-expand it in chemical potential, that we get a set of susceptibilities at zero baryon chemical potential. We demand that that matches what was seen on the lattice. And we also, of course, demand sort of basic thermodynamic consistency. So the speed of sound always remains positive. So we impose standard thermodynamic constraints, and we impose that we can connect this to a hadron gas at low temperature. That does limit what we can do, because if we try to take a critical point and we push it too close to the chemical potential, to the temperature axes, then of course we're having trouble matching the lattice QCD susceptibilities without, you know, producing a lot of non-analyticity in these so-called regular temperature coefficients. So in this paper, we somehow study what can be done. Where can we put the critical point and how strong could it be? And what you see on this plot is a sort of illustration of that. So this is an equation of state that we constructed. So we have a set of software tools that effectively allow you to put this point in different places and get an equation of state that satisfies all the known constraints along the temperature axis and satisfies thermodynamic consistency and can be matched to a hadron gas. And again, that limits to how far you can push it to the left, but there are a variety of choices that are perfectly consistent with everything we know. What you do, however, see is that the kind of equation that you get does have a non-analyticity, but these non-analyticities are not actually very, very strong. So there is a peak in the baryon susceptibility. There is a non-analytic dip in the speed of sound, but these are actually not super large. They're relatively localized, and they're not very strong. In order to be consistent with lattice data, if you put a critical point at, say, 300 MeV baryon chemical potential, you can push it further away, and then you're allowed to make it a little bit stronger. So an equation of that, like that, can now be used in a variety of ways. And in just a little bit, we will use it to do actual hydrodynamic simulations. But one of the exercises you can do with it is, for example, to compute something like the critical bulk viscosity. The critical bulk viscosity is a quantity that has a part that's completely universal, but then it has a non-universal overall coefficient that depends on the actual equation of state of your system. Roughly, that non-universal part knows how strongly the critical mode actually couples into the pressure of the system. But once we construct an equation of state like the one we just constructed, we do know what that coefficient actually is. So it involves these kind of mapping coefficients that were on my earlier slide. And then it contains a purely universal part that knows about the relaxation rate for the order parameter. Okay, so this is an exercise I did with the postdoc and together with Lattice QCD. And what we find is that the critical bulk viscosity, so it's eta over S, it has a scale that's set by eta over S. So if eta over S is of order 1 over 4 pi, this is of order 1. Then it has a universal divergence. It scales like correlation lengths to the 3rd power. And then it actually does depend on the way you map one phase diagram to the other. So this actually is an angle that would be 0 if the first order trace transition comes in exactly horizontal. And then it has an overall coefficient that you can compute. And it actually depends on whether you are on the first order side of the phase transition or on the crossover side. So the coefficient on the crossover side is actually relatively small. It's on the order of a few times 10 to the minus 4. So what you see from this is that, and in practice, this coefficient is this critical enhancement. So in principle, it becomes arbitrarily large, but as you will see later, in practice, it's hard to get the correlation lengths to grow much beyond, say, a factor of 2 over the non-critical background. So this is an enhancement, which in practice is never really much bigger than a factor of 10. So overall, there is a critical enhancement in the bulk viscosity, but at the end of the day, it never becomes very large. It never becomes much bigger than the shear viscosity. And this is a theme that you will actually see later on, that critical fluctuations are potentially important, but that their feedback on things like the equation of state actually tends to be small in practice. Okay. So this brings me to doing an actual somehow hydrodynamic treatment of these collisions that we explore in the beam energy scan. And one of the first issues one has to address in this context is the issue of initial conditions, which becomes more difficult as you go to the lower energies. So what you see on the left is a simple kind of Glauber Monte Carlo kind of slide. So this is, a space-time picture of a heavy ion collision at 200 GeV, where you really have these kind of pancakes. And then there's a similar collision at 20 GeV, where you now have a more extended kind of projectile and target. And what the more extended projectile and target, of course, imply is that it takes longer and longer for the two nuclei to interpenetrate, and so that there is a longer and longer variation in the time at which the first collision occurs. And so this is a plot of this kind of overlap time as a function of the beam energy. So at 200 GeV, that's kind of short, but as you go all the way down to 10 GeV or so, it becomes quite long. It becomes on the order of 3 Fermi or so. And what that means for a hydrodynamic treatment, of course, is that you can no longer just initialize the system and then take that initial state and feed it into hydrodynamics. If you wait until all the first collisions have taken place, then the hydro stage in other parts of the system is already almost over. So in practice, you somehow need some kind of initial state model that can continuously feed energy and momentum into the hydrodynamic evolution. And so in this report, we discuss a model that was constructed by Bjorn Schenke and Chun Chen, where they effectively use a string model to do this. This is not necessarily because we're somehow strong believers in a string model, but a string model can at least handle the sort of basic constraints based on causality and energy momentum conservation and just reproduce at least the correct space-time picture of a collision at the lower energies. So this is a simple model. It's described in more detail in the report and in the original paper, which I refer to here. But the idea is fairly simple, that indeed you track these first collisions, that when the collision takes place, you put a string between the two wounded nucleons, then the string decelerates, you have some kind of equilibration time, and after that equilibration time, the string now feeds energy momentum into the collision. And what this picture tries to show is, again, the difference in the space-time pictures that emerges at the high energies and at the low energies. So at the high energies, so on the left, by the way, this is just, time and space. On the right, this is now space-time rapidity and proper time. And at the highest energies, at least, at central rapidity, it's essentially a universal proper time. But you see that at the lower energies, it's now a very complicated looking source. Okay. And then there's a set of hydrodynamic calculations where we see what this implies for, say, the rapidity dependence of the net protons. This is kind of a busy plot again. Let's maybe just look at the plot here up on the lower left. So this is the most central part. And the black curve is the highest energy. So this is 200 GeV. Again, there's still a dip in the net protons at central rapidities. But as you go to the lower and lower energies, so the blue points is now the 7 GeV, you see that the net protons are actually peaked at central rapidity. You also see that, by the way, right now, the data on this are still somewhat sparse. So for now, at the lower energies, there's only a data point at central rapidity. But clearly, this is a sort of, number one, it's a reminder that it's important for the hydrodynamics to actually construct a suitable initial state model. And it's also a reminder that when we study, so this is the net protons of which we study fluctuations, that the underlying event is really changing quite a bit as you go to the lower energies. So here I already in principle showed, a final state of a hydrodynamic evolution. This is more of a reminder of what a trajectory might actually look like. So we took this hydrodynamic evolution, we took the initial state we just constructed, but now we also used this equation of state that was constructed by the BES collaboration. So this is an equation of state that now has a critical point, which for this particular calculation, we put even lower in baryon chemical potential. We put it somewhere at 250 MeV. Okay. So these are now average trajectories from a 3+1 viscous hydro calculation that was constructed by Chun Shen. And what this shows is that, number one, you get these kind of shapes that people have probably seen. They're, at least in an approximate sense, trajectories of constant entropy per particle, here shown in different regimes of space-time rapidity. And what this plot is simply meant to show is that putting in the full equation of state does, of course, modify these trajectories, but not very, very strongly. In particular, if you really sort of average them over some range of rapidities. So you see an effect of putting in the critical point, but the effect on the actual trajectory is not very strong. Okay. So finally, I want to come what is maybe the sort of central part of the talk, which is to now really look at critical fluctuations. So the critical fluctuations, of course, in principle, are also part of the fluid dynamics. Fluid dynamic variables can fluctuate, and fluctuations can become large because the equation of state has a critical point. And at least schematically, what the equations of motion for a critical mode, say the entropy per particle, look like is something like this, that there is a diffusion equation that describes the time evolution of this variable. It has a purely diffusive piece governed by some kind of transport coefficient that could be a thermal conductivity. It has a piece that is just advection by the background fluid. So there's a coupling to the momentum density of the fluid. And there's a noise term that is a source for these fluctuations. The noise does not become strong as you approach the critical point, but the equation of state becomes very soft. So a given amount of noise can cause more and more fluctuations as we approach the critical point. That is ultimately contained in some kind of free energy functional. So this is a very schematic free energy functional. So here, this is the momentum density of the fluid. And this is now the part that's related to the order parameter. In general, because the order parameter can become very soft, near the critical point, you should include gradient terms in the free energy functional. And then this is just an expanded version of this kind of Saint-Just functional that I mentioned earlier, that any equation of state will have a quadratic term, possibly a cubic term, a quartic term, and so on. And what happens in the vicinity of a critical point is, of course, that this kind of restoring force goes to zero, and fluctuations can now become very, very large. And what we do in a hydrodynamic simulation, at least in principle, is, again, we take many, many realizations of that noise term, and we just average over them. And the simplest choice of a noise term that's consistent with fluctuation dissipation relations is a noise that's completely local in space and time. So that's this kind of delta correlated noise that we always talk about. So this is a noise functional like this. It's purely Gaussian. It's purely local in space and time. And its strength is completely determined by fluctuation dissipation relations. So there are a variety of ways to actually do this in a heavy ion kind of environment. And to some level, we've explored them all, but I will talk in more detail about the last of these options. So let me just briefly go over what the options are in principle. So in principle, for example, you can just take the stochastic kind of fluid dynamics. So here I wrote a stochastic diffusion equation and just solve it by sampling many, many realizations of this kind of Gaussian noise. So I have a diffusion equation. We know what the free energy functional or the equation of state are. I have my delta correlated noise, and I just add that noise term to an existing hydrodynamic code. So in principle, I was always tempted by the fact that this is just kind of one line of code in your hydro code, because you just take an existing code and you just add the noise. And that should be all you have to do, in addition to actually putting in a critical equation of state that becomes soft in the vicinity of a critical point. But actually dealing...
Thomas, there is a comment from Edward Shuriak. Edward, do you want to make your point?
It is just a small comment. So Landau famously said that at second order transition, the coefficient of psi square vanishes, right? The mass step. But he keep the coefficient of the fourth power constant. That was a mistake. If you do scaling with three-dimensional scaling, the first coefficient, who is non-zero, is coefficient of the psi to the sixth term. And this is borne out from also lattice and also the studies of renormalization group, functional renormalization group. So the first significant term in the Ising is the sixth term.
Yeah.
And that makes fluctuation larger.
Yeah. So indeed.
So maybe you can put it in.
Yeah. So I should have put it on this slide, but what we do for actual calculations is indeed this Saint-Just Ising model, which indeed has the kind of properties that you mentioned, that the sixth order term is actually quite relevant. And in fact, it has all the terms that, you know, it's some...
No, it has all the terms, but this is the first non-zero at the critical point. Right. Okay, that's...
Yeah, so this is indeed, again, the first option to do this is to just take an existing hydro code and just add the noise. And what a lot of people have discovered is that using delta correlated noise, even away from the critical point, induces very large fluctuations that for the most part just average out to zero, and at next order give very small corrections to the equation of state. And that is just a difficult way to do business. And we've looked into it, and I think it's still an interesting approach, but it's actually not that easy to apply in practice. So formally, what's interesting, what's useful to do various analytic calculations is the fact that stochastic fluid dynamics can be written in terms of stochastic effective action. So I can use some kind of action functional whose equation of state is just stochastic fluid dynamics, and that has an auxiliary field that effectively provides a source for the noise that the delta correlated noise supplies in stochastic fluid dynamics. And what is interesting about these stochastic effective actions is that you can just use them, you can just study them with the tools of ordinary field theory. So you can study them with Feynman diagrams, you can study them with Dyson-Schwinger equations, and so on. So there are a number of important analytical results that were obtained for ordinary fluids and now for QCD fluids just by using these stochastic effective actions. But of course, what all these tools like Feynman diagrams always use is that you have a very simple background about which you can just determine what the propagators are. So in a real heavy ion collision, that of course becomes difficult. So in a real heavy ion collision, in principle, there still is a set of propagators, but it's hard to write them down analytically. And by the time you construct them numerically, you might as well do full numerics. So this is an important tool for many analytic calculations. But if you want to study a heavy ion collision, this is maybe not the tool to use. So a tool that has been used by many people now is that instead of a stochastic approach, you effectively do the averaging analytically, and you do the averaging at the level of constructing endpoint functions. So you can construct, for example, the Fourier transform of the two-point function. This is some kind of Wigner function that is labeled by a coordinate in space and time, and it's labeled by the relative momentum of the two order parameter phi. And you try to do this kind of averaging analytically and determine a non-stochastic, a deterministic equation of motion for this kind of two-point function. And this is the sort of two-point function that you would eventually then measure in experiment. And the kind of equation of motion you get, given that the equation of motion for the underlying field is just a diffusive equation, is again a diffusive equation that has some kind of relaxation rate that may depend on the momentum, and that describes the relaxation to some kind of equilibrium two-point function. And what in practice we have now studied in quite some detail is that you take that kind of deterministic equation for a two-point function, you let the two-point function be advected by the background fluid, and then you include the back reaction of the non-equilibrium behavior of that two-point function. So the fact that the two-point function is not equal at any moment in space and time to its equilibrium value, and you put that kind of back reaction back into the thermodynamic variables, so that the thermodynamic variables, at least in principle, know that your fluid is off of equilibrium because there is slow relaxation of the two-point function to its equilibrium value. And so that kind of approach has been termed Hydro Plus, and that is the approach that's maybe most mature in doing actual comparisons to heavy ion data. So that's what I will show in the remaining slides here. So this, again, a brief summary of what Hydro Plus is. It's a relaxation equation for the two-point function for this kind of Wigner function of the order parameter. It includes a back reaction of that two-point function onto a non-equilibrium pressure. So the pressure depends on, say, the equilibrium energy density of the fluid and on this two-point function. I now have to specify what the dependence is. So we specify that dependence through defining a non-equilibrium entropy. So this is a non-equilibrium entropy functional that shows that, you maximize the entropy if the two-point function relaxes to its equilibrium form. In that case, of course, the non-equilibrium entropy goes to 0, but if the two are not equal, then there will be a non-equilibrium contribution. What this kind of Hydro Plus requires is some kind of model as to what that equilibrium two-point function actually is, as well as some kind of model as to what that relaxation rate actually is. And for that, we effectively rely on universality. We assume that if this is indeed critical behavior, that these two quantities have the same form up to a mapping onto these Ising variables that they have in an ordinary fluid. And so these kinds of forms are indeed then forms that you can compute, either that you can study in experiment for ordinary fluids, or you can compute them using these analytic approaches, like just computing Feynman diagrams from an effective action. For ordinary fluids, this is an exercise that people have engaged in for many, many years. So there is a sort of standard form, this kind of Ornstein-Zernike form for the two-point correlation function. And again, there is a kind of standard critical form for the order parameter relaxation rate. So it's purely diffusive, so it goes k squared. And then if you're close to a critical point, it becomes slower. So it approximately goes as k to the 4 if the correlation length is very large. And then if indeed we take the order parameter to be the entropy per particle, then the overall normalization of this thing is given by the specific heat at constant pressure. So this is, again, effectively something that comes from your equation of state. Okay. So this is now an example of an actual calculation. It's not a completely realistic calculation. So for simplicity here, the background flow was just taken to be Kupser flow, but at least it is a calculation where you have expansion in both the longitudinal and the transverse directions. And what this plot shows is this kind of Wigner function. So here is a function of the relative momentum in units of inverse Fermi. And this is shown as a ratio of the Wigner function to its kind of non-critical version. So as you approach a critical point, so this is here as a function of time. So it's initialized to just be equilibrium at some initial time on the order of a Fermi or so. And then in this particular calculation, the correlation length becomes maximal at a time on the order of 3.5 Fermi or so. So at this point, the equilibrium two-point function, this is this dashed curve, would now be very, very large. But we're solving a relaxation equation. And of course, the relaxation rate, again, you saw that previously, just scales as momentum. So this is diffusive relaxation. So this implies that relaxation is slow at low momentum. It becomes very fast at large momentum. So you get this kind of behavior that at large momentum, the correlation function just tracks the equilibrium behavior, but at low momentum, you fall behind. And indeed, at zero momentum, there's just no evolution at all. The correlation function cannot evolve at all at very low momentum. So what you see in this kind of plot is indeed some kind of memory effect that at low momentum, in principle, the system is evolving, the correlation length is becoming large, the two-point function, the fluctuations want to become big as well, but they can only become big at larger momentum where relaxation is faster, and they cannot become arbitrarily large at low momentum, where in principle, the divergence is the strongest. Okay. In principle, as you pass the critical point and the correlation length now returns back to its equilibrium value, you should kind of see the opposite effect that now fluctuations are larger than predicted by the equilibrium behavior. This is a little complicated plot because here this is plotted at the center of the collision, and the order parameter is proportional to entropy per particle. So what is happening here is that the density is now becoming very slow. So this is kind of a funny plot. So this is maybe a little bit easier to see on the left-hand side, where we clearly see this kind of memory or lapse behavior. Okay. So this was now, so previously this was at the center of the collision. So at r equals to 0, and it was shown as a function of the momentum. So in this plot, we now fix the momentum to be something like 200 MeV. So we did this because if you look at this plot, this is roughly where the enhancement occurs. So now we fix it to 200 MeV, and we show as a function of radial position where it actually is that this two-point function peaks. Okay, so this is again shown at different times. This is at 3 Fermi in red, and then the latest time is 15 Fermi, which is in blue. So you see here that effectively the place where the enhancement and the fluctuation occurs as a function of time, it slowly moves inward. And what you also see is that, again, the dashed curve is the equilibrium expectation given the value of the correlation length, and the red is the actual solution of a relaxation equation. So again, you see a kind of memory effect that since the whole thing is kind of moving inwards, the equilibrium is ahead of the actual solution of a relaxation time equation. And what the right shows is that in an actual collision, the dominant effect is actually not so much this relaxation in memory. The dominant effect is that you have all this radial expansion, so that the advection effects, the fact that the fluid is pushing this correlation function out, is actually the dominant effect. So again, once the advection is included, the red curve is the full 2-point function. The dashed is the equilibrium expectation. At early times, again, it's dominantly this kind of memory behavior, but at later times, the difference between the equilibrium and the actual solution of the hydrodynamics gets more and more, the two become more and more different because there's all that radial expansion going on. What we also find, again, one of the features of this kind of hydro plus evolution is that this deviation between the actual 2-point function and the equilibrium behavior is fed back into the pressure and the entropy of the system. But we find that in an actual evolution, this back reaction is really kind of small. That's a combination of two effects. One effect is the fact that the actual enhancement in the correlation function is not very large. It's a sort of factor of 2 or 3. So even if you have, correlation over bare correlation to the 3rd power, it's never more than a factor of, say, 8 to 10. And you have to compensate. It's like a loop effect in quantum field theory. There's sort of factors of 1 over 2 pi that are floating around. In addition to that, the entropy of the background quark-gluon plasma is really quite large. And as a result, or the entropy density is really quite large. And as a result, this kind of back reaction at the end of the day is actually not that important. Ultimately, for the modeling of a heavy ion collision, that's actually a useful effect because it means that this complicated hydro plus kind of evolution may not actually really be necessary, that in some sense we can maybe use even simpler approaches where we just do the hydrodynamics first, and then we propagate a 2-point function, a 3-point function, and a 4-point function separately. Okay, that would be a simpler approach.
Thomas, there is a brief question by Bernd. Bernd, go ahead.
Yeah, once more, a quick question, Thomas. When you fix the momentum in the right plot, is it fixed in the lab frame or in the co-moving frame?
So there is a kind of, so again, in principle, this is a kind of Wigner function where we center, where did I define this? Oh, here. Where we center on some kind of point in the fluid and then we Fourier transform in relative coordinates. And that should, of course, be the local rest frame of the fluid. And that was in a relativistic fluid that actually requires a little bit of thought, exactly how you define what you mean by an equal time correlation function in this expanding fluid. And that was studied more carefully quite recently by Curvature, Misha, one of Misha's postdocs, and so on. So there's a detailed paper, which I think I referred to later, where this is explained. But certainly what we have in mind is that you define an equal time correlation function in the local rest frame of the fluid, and then you Fourier transform with respect to that coordinate.
We also have a question from Scott Pratt.
Sorry, I see that you actually wrote it on the slide. I was going to say how small is small, and there it is on the slide, 10 to the minus 4. So that's very small. So that answers the question.
Okay, good.
So the final step, of course, is so something like Hydro Plus or another one of these kind of deterministic approaches provides you with a 2-point function for the critical mode, say, so taken to be the entropy per particle. But of course, what you observe in an actual experiment is, particles. So the question is how you convert these kinds of results for, say, these Wigner functions into actual 2-point correlation functions for particles. And what we've done in kind of existing work is a very simple model that people have used before, where you assume that there's a coupling of the critical mode to the mass of the particle that occurs in an ordinary Boltzmann distribution function. So you write down a model for the distribution functions of particles. So this A just labels species as a function of position and momentum, which is a background that would just come from an ordinary Cooper-Frye, and then some kind of coupling with a certain strength to the critical mode, which is this S hat. And then, of course, you can propagate that through to endpoint functions, which would effectively give you a particle, the variance of a particle multiplicity as an integral over the freeze-out surface of a kind of source function, which again is just a coupling of the distribution function to the critical mode, and then this kind of two-point function that an approach like the deterministic approaches for the endpoint functions or Hydro Plus would give you. Okay, so then it's just a more complicated freeze-out procedure that would correspond, that would take this two-point function and convert to multiplicities. And again, here's an example that we show in this report. So on the left plot, you see an actual two-point function on the freeze-out surface. So the way this is plotted here is that we take a freeze-out surface that was just generated as a freeze-out surface at a constant freeze-out temperature, and then we look what the actual two-point function looks like for different radial positions on that fixed freeze-out surface. So in principle, the equilibrium one, again, is just this relatively simple Ornstein-Zernike kind of form, but the actual non-equilibrium distribution function is more complicated, including due to all of these advection effects, it actually can become negative, which is usually what we didn't see in the pure equilibrium expectation. In addition to that, what you see, if you do this purely in equilibrium, again, the actual enhancement in the correlation function can be kind of substantial. So it can be factors like 10 or so. And so if you do it in equilibrium, you're of course extremely sensitive to exactly where you freeze out. If there's a critical point at a certain temperature and you freeze out very close to that, you can get a very substantial enhancement. If you do it further away, then the enhancement would be much smaller. But now we do an actual evolution of the system. So the actual correlation function that you have has all of these memory effects. It has all of the effects due to advection. And what you find as a result of that is that it doesn't actually depend all that strongly anymore as to what you assume where the freeze out occurs. So these are two different freeze out temperatures, but the actual enhancement in the variance of the particle distribution is, number one, it's of course smaller, so you never see it as factor 10 anymore. It's only a factor 2 or so. But the good news is that the sensitivity as to where exactly you freeze out is now really quite small because we do the full non-equilibrium evolution. So finally, I wanted to mention a few things that somehow I didn't have space to show. So number one, so this is a freeze out procedure that we use with these Hydro Plus simulations. If you actually do stochastic fluid dynamics, then in some sense, you don't have to do this. You can just use the ordinary Cooper-Frye. You have a background fluid that really does fluctuate in density, in energy density, in temperature, and so on. So you can do the stochastic simulations, and there was some work by Bloom and collaborators and by the McGill group. But now what you need is a freeze-out procedure that can actually preserve these local fluctuations in the density and entropy density of the fluid. So what that requires is a kind of microcanonical particlization, because you want to avoid that your freeze-out procedure washes out the fluctuations that the underlying fluid contained. And there was some significant work done on that by Dima Olichenko and Volker Koch, which is this local microcanonical particlization. In addition to that, we also investigated a number of hadronic afterburners that contain more physics that becomes more relevant at the lower energies. In particular, you would like to have hadronic afterburners that can contain potential mean field effects. So, you know, for example, when we now in this Hydro Plus freeze out, when we include the connection to the critical mode, we effectively have a kind of mean field contribution in the freeze out. And so if you want to smoothly connect to a hadronic afterburner, in some sense that hadronic afterburner should contain the same kind of mean field effects. And that's something that we have studied. In particular, Agnieszka and Volker have studied these kind of things together with Scott Pratt and others. Finally, of course, it's still true that uncritical contributions to these various fluctuation observables are important. And again, a number of people have studied that, including Levchenko, Volker, Chunshen, and others. And finally, it's of course our goal to incorporate all of these tools that we've collected into a kind of full Bayesian analysis framework along the lines of what was, for example, done by the Duke group. And that, again, is an effort that's actually still in progress, involves people like Chun and Scott and so on, so that there will be a full best Bayesian analysis framework. Okay. So finally, in order to conclude, so we're certainly looking forward to actually seeing the full data. In the meantime, we have developed a set of tools that can be used to study fluid dynamics at the beam energy scan energies. So in particular, we've looked at initial state models. We looked at full 3D hydro, including baryon number diffusion. We've looked at afterburners that actually contain mean fields. We've looked at microcanonical particlization and so on. And we certainly studied a number of tools that can be used to study the non-equilibrium evolution of fluctuations. And we believe that there's actually some simplifications that do occur. In particular, the back reaction of the fluctuations onto the equation of state and the trajectory of the fluid are not actually very large. The growth in the correlation length, of course, is also not actually very large. In the end, it's still modest. It's, sort of factors of 2 in the correlation length and factors of a few in actual fluctuation observables. We're still working on extending these deterministic equations of motion for the higher order cumulants so that we can also study things like skewness and kurtosis. And we would also emphasize that just studying the integrated cumulants is not really the end of the story. If at the end of the day, the enhancement in integrated cumulants is not that large, of course, you can potentially benefit from actually studying more differential observables, meaning to actually study the correlation function as a function of the relative momentum of the particles. And given that we expect these enhancements to occur at sort of the inverse correlation lengths that you actually attain, it may indeed be interesting to study that at a relative momentum of, say, 50 or 100 MeV. So to do something like HPT-like correlations, but not at 5 or 10 MeV, but study at, say, 50 or 100 MeV. Okay, well, thank you so much.
Thank you very much, Thomas, for this very nice overview of the best collaboration results. Do we have questions for Thomas? At this point, you can just raise your hand if you have any question. Deborah?
Yes, hi. Could you go back to the slide where you show the hydro trajectories and the critical point on the phase diagram, please? So what was the main takeaway here is that the hydro trajectories are not that affected by the critical point?
Yeah, at least that's somehow the back reaction of so the number one, there is some distortion, obviously, and we actually already showed that in the paper with Paolo, that there is some distortion of the constant entropy per particle trajectories due to a critical point. That distortion is already not very large. I mean, in principle, there is, for example, a kind of first order jump in this, but the first order jump is not super large. But if you now put this into an actual hydro and you somehow average over some regime where locally the conditions obviously change, is that these average trajectories, the differences are even smaller. So obviously, on the left of the critical point, you barely see it. And then there's a relatively small effect here. And that is in some sense, sort of smaller than your uncertainty into where you actually are in the phase diagram. So I think it's another illustration of the fact that the sort of back reaction is not actually very big.
But how sensitive would this be to the critical region itself? Because I don't know much about the hydro side, but I worked a lot on the equation of state. And we know that if you put the critical point at 250, which is what it seems like was done here, that has to be a very weak critical point. Like you said, you can't have too much of a critical effect if you're that close to the t-axis.
Yeah, so this is indeed part of the story, of course, here. So again, in the paper with Paolo, I think we don't show 250, we show 300. And there's some distortion in the constant entropy per particle trajectories, but that is already not very large. And I think all I'm saying here is that there's some distortion that you can already see from the critical equation of state. And that is, of course, constrained by how close you put it, because the lattice data constrain you in not making it very big. But then there's some additional smoothing that comes from actual hydroevolution.
But wouldn't it be possible that if you, let's say, move the critical point to higher densities, and now you can adjust those equation of state parameters to where you have a much stronger critical point, how sensitive would the hydro be to that?
Yeah, I mean, so this was at 20 G, does it say? Oh yeah, so this was at 20 GeV. So again, you go lower in energy, you can push the critical point to the right, you can make the effects larger. I think this was a little bit of a compromise. Of course, all the hydro modeling gets more difficult if you go to lower and lower energy. So I think here the 20 GeV was a little bit of a compromise to be in a regime where you actually have a relatively long hydro phase and you can pull the critical point closer. But yeah, I mean, what you say is certainly correct, that if you push the critical point to the right, you can make your effect bigger.
Okay, thank you.
Okay, next question by Edward.
I just want to make comment on this. So as Thomas have shown very well, the effect of critical point on average behavior of hydro, average evolution, etc., is very small. So the idea that you just change the whole nature of events near critical point is not going to work. So the idea was to look at higher cumulants and at fluctuations. And I want to say that in several papers in the last few years, we look at another observable. So if we have fluctuations on the scale of 1.5 Fermi, it is difficult to measure from, unless you do correlation function, as Thomas said, at the final state of hadrons close in space, which is difficult to do. So study these hydrodynamical fluctuations is really hard. It is not yet converged. We propose that these fluctuations on that scale will affect correlation of nucleons, and in particular production, pre-clustering of several nucleons, and then production of light nuclei, which would be more sensitive to this type of fluctuation. So for example, we focused on 4 nucleons, and 4 nucleons have 6 potentials between them. So if effective potential changes locally, it is an exponent, and there are 6 of them, etc. So this correlation of nucleons, which will go eventually to light nuclei, will be enhanced very much. So I think this is a very promising observable. So this particlization or hadronization include correlation of nucleons, which we actually observe in form of light fragments at the end.
Yeah, I find this actually amusing in the sense that in some sense we're arguing that the relevant observable for the QCD critical point is actually not so dissimilar from the relevant observable to the old nuclear gas, nuclear liquid gas critical point, which is that you should look at cluster distributions.
Yes. Yeah, okay, so
I bet Scott has a certain sense of deja vu. I don't know what that sound is. It's not me.
not me either. Okay, thanks, Thomas.
Thanks.
Okay, next question by Ulrich.
Yeah, it's a comment on Deborah's question. Yes, you can make the equilibrium effect, critical effects bigger by moving the critical point further out in mu. But that also increases the effect of critical slowing down, which means that the hydrodynamic system doesn't follow the critical enhancements to their peak values, but it saturates and stops growing well below that. So the hope for making the critical effects much bigger by moving the critical point further to the right in the phase diagram are really limited.
I see, but that's in the framework of equilibrium effects only, right? So you're not studying anything like.
The point is that the fact that you are dynamically evolving and that the evolution of the critical modes that can show critical dynamics is slowed down means you pass through the critical region before the critical effects ever have grown very big.
I see. Okay, thank you.
Okay, next question by Nu.
Yeah, hi, Thomas. Thank you for this summary, and thank you for the best collaboration. Actually, for this reason. I have two questions. One is your discussion focused, as far as I can see, focused in the momentum space. Any effect if in a critical behavior to the configuration space? Because in reality, critical point happens also should affect, for example, the size of the fireball, the correlation between particles. Did you study this in the effort?
Well, the size of the fireball, I mean, again, that's somehow radial expansion driven by the equation of state. And I think what we're saying is that in principle, of course, people have this idea that, oh, there's a critical point, the speed of sound goes all the way to 0, so you should see a dramatic effect. And I think what we're saying, and okay, many people have said over the years now, is in practice that does not happen. So this kind of back reaction that there's a dramatic difference in the, say, radial expansion of the system, this does not happen. Now, the kind of correlations that we discuss in momentum space, there are, of course, again, correlations in coordinate space as well. I mean, there are effects on maybe higher order fluctuations in an observable, like, higher VNs and so on. But again, I'm not sure that this is quite the way to go, because these are very strongly damped and they're mainly governed by the background evolution of the fluid, by fluctuations in the initial state and so on. These kind of critical fluctuations at the end of the day, they're actually relatively short range in real space because everything is somewhat driven by the expansion of the system.
Okay, thank you. Now, my second question has to do with the experimental and theory program. We are still in the midst of analyzing BES-II data. And we, of course, need a strong support from theory side. So the question is, what is the future of the BEST? Do we expect a BEST plus or BEST plus plus?
Yeah, the joke in the collaboration was actually maybe we should have second best. And then we realized that by proposing second best, we maybe don't really increase our chances of getting funded. So yeah, I mean, I don't know, as the experts may know, there actually is a call in the US for new topical collaboration proposals. And we certainly want to continue in some form because, again, we look forward to the data. We're actually not completely done with putting the tools together. So there's certainly a group of us who is somehow fiercely determined to continue in some way. And we'll let you know as soon as we know exactly how that will happen.
Okay, thank you.
Bernd?
Hey, Thomas, thank you. That was a wonderful overview of that component of the BEST collaboration work. I really enjoyed it. My question is the following. In the case of heavy ion collisions, one is not tracking one system for a long period of time where one monitors the fluctuations, but one is actually looking at many, many realizations of the system and looks at the fluctuations across that ensemble. Now, there you have it, or you already mentioned it, you have two sources of fluctuations. Those that come from the initial state, that is in the creation of the system, and the other one comes from the dynamics of the system itself. And of course, you're interested in the latter ones, in particular those associated with critical behavior. So my question is, has the BES collaboration looked at which observables, which variables minimize the influence of initial state fluctuations and maximizes the effect of critical system fluctuations?
Yeah, as I mentioned, so in some sense, the actual calculations that I showed to you, a few minutes ago, were calculations where we assumed that by some miracle, the two-point function actually started in equilibrium, and then we studied deviations from equilibrium, critical, deviations that occur as the system evolves. The real world is obviously more complicated. The two-point function should have started from some initial two-point function that's really reflective of fluctuations in the initial state. I don't actually know that we necessarily know how to model this super well. The one thing I would say is that, again, we expect, based on fluid dynamics, that at high momentum, everything equilibrates very quickly to thermal equilibrium anyway. And at very low momentum, it cannot evolve. And then there's that magic regime in between where you can have critical fluctuations that grow, which is the magic, whatever, 1 Fermi or so, and then the corresponding inverse, which is 50 MeV or so. So I think if indeed you look at that kind of momentum scale, you would automatically be relatively independent of what exactly you started with. But it would certainly be useful to study that in more detail by using, say, different models as to what an initial two-point function or initial 4-point function might look like.
Right, but if you want to do that, I mean, the main reason why one expects initial fluctuations to, be not overly dominant is because there's dissipation, and though the dissipation has the longest time to work on those, except when they are in conserved quantities, of course, and these are exactly those that you look at in the search for the critical phenomenon. So I think it would really be nice to see an investigation, at least, how the dissipation affects these. In particular, when I think about it, is you mentioned the clusters. The clusters are not just two-point correlations; they are multi-particle correlations. And so one of the questions would also be, can more than two-point fluctuations help you in that respect? Especially if, as Edward points out, it's really the first term that comes in is the 6th order term of the thermodynamic potential. I could imagine that multi-particle fluctuations actually are equally important and useful.
Well, I mean, so as I certainly said, I mean, the first exercise to me is to at least extend what we currently have to 3- and 4-point correlation functions. And there are some ideas as to how we can do this. And certainly, for example, if you look at the hints that are in the kind of BES-I data, we didn't actually see much in kind of 2-point, in just the variance of the particle distribution. To the extent that something was happening, it was in the kurtosis. So you would like to have a dynamical model that could potentially accommodate a phenomenon like this, that say the 2-point function has actually relaxed back to equilibrium, but there's memory of an enhancement in the 4-point function. So you certainly need a dynamical framework that's capable of handling a situation like that. And then the other thing that you mentioned that, you should really study in more detail as to how, in practice, you integrate over some window of rapidities when you do this. You should certainly study in some detail exactly how that depends. And at least in principle, I would argue that we have some tools to do this.
Can I
Yes.
say something about this? What Björn asked, first of all, about memory of initial state. We know that for harmonics with azimuthal number m, there are sounds and they're damped as exponential with viscosity times m squared. And that acoustic systematic was checked very well by Roy Lacey and collaborators, and it works. So it goes like this, and the memory of initial state decreases exponentially with m squared up to roughly 7 harmonic, up to m equals 7. And after that, there are, of course, big error bars. But if you go, for example, to LHC, which have higher statistics, after 7, they stop dropping. It started being kind of level, the amplitude of harmonics. And that may be the thermodynamic fluctuation independent on the initial state. So if one combine higher harmonics and m of the order 10, which correspond to domains of the size of 1 to 2 Fermi inside the system, that is the right scale. And combined with this rapidity, as Thomas just mentioned, etc., that can actually provide eventually measurement of thermodynamical fluctuation in the system. So I'm saying up to m equals 7, it is dominated by initial state, and then it dies. And after it dies, we see something else. There's something else of thermodynamical fluctuations. Must be. And then we look at those, and those may be sensitive to critical point.
Yeah, it's also true, by the way. I mean, one thing that I historically had the wrong intuition about is you would think that if you look as a function of rapidity, that there's some rapidity window, which is whatever, 1 unit, which is kind of just thermal smearing in the final state. And that once you go beyond that, you somehow look further and further back in time. Mm-hmm. But if you just solve a diffusion equation on top of a Bjorken background, you see that the two scales are actually pretty complicated. Since the longitudinal expansion is so strong, you can never actually diffuse very far, even if you start very early. So these two rapidity windows are actually quite comparable, the sort of thermal smearing one and the one that comes from diffusion in a Bjorken background. So,
right. So we cannot, we must go to large M. If we're interested in fluctuation on scale 1 Fermi, and you compare it to circumference of the fireball, it becomes clear that you need to go to higher harmonics in phi. Because otherwise you average over a whole big surface, right?
Yeah. Okay, next question from Scott.
Hi, Thomas, could you show the slide that showed the correlation, as a function of distance, it frees out and it, went positive? Yeah, that one on the left there, beautiful. So I find that one really useful, to think about how big the signal is. And so that distance at which it changes around 4 Fermis, assuming the freeze out is about 7 Fermis or so, it suggests that that the window in which, if you look at a big window, you'll catch both the charge due to charge conservation, you'll get nothing because you'll capture both parts. And what you want to see, you want to separate, look at a small enough window to get the hump, but not the deficit. And that looks like it's going to be like a half unit of rapidity on that order. But then another thing, from my experience with, comparing many different kinds of correlations and fluctuations and what have you, is that it's nice to gauge the strength of it by asking, let's just look in that hump on the left. If I see a baryon, that suggests there's some extra chance of seeing some extra baryon number, say within that 3 or 4 Fermi. And what is it? If I were to integrate that bump as to say, like, what fraction of an extra baryon do I see given the observation of a baryon, like taking the correlation function, divide by just the density, and then integrate out to delta X equals 3 or 4. If that number is less than 0.1, it's very hard. If it's bigger than 0.1, you should be pretty optimistic. So it's it's in that scale when you integrate it. But I'm not sure, if I should integrate x squared dx or or just look at the area under it, looks like about, you know, like it's about 0.04 or something. Is that the right scale?
Yeah, I don't know. I should provide one warning. So you always look at these correlation functions of, say, a conserved charge, where there is a kind of negative screening cloud. This correlation function that's shown here is entropy per particle, which is not a conserved quantity. So the equilibrium one actually does not go, the equilibrium one is the dash one, never goes negative. So this funky negative behavior.
So this is not a density correlation.
No, I mean, of course.
Oh, I see. They're in the blue text there below. I didn't have time to read all the way down there. Okay.
It eventually gets translated, you know, by this, we couple the critical mode to the conserved baryon number of the system. But the underlying correlation function that was actually propagated through the hydro was entropy per particle.
You know, but Hydro Plus also can, you know, give you a density fluctuation, and it also conserves charge, so it should have the same visual sort of qualitative behavior. But I would just say, you know, as a if that were the density correlation, what it's good to understand what the size of the peak, integrated size of the peak is, in the question of, you know, if I see a baryon, how much extra baryons do I see within that first peak? And that's just because it's good to have an idea how big it is compared to all these different kinds of background that are going to come up.
And what's the probability to see 4 baryons in the same little cell? This is our hypothesis.
Yeah, exactly.
Right.
Okay. Oh, still no?
Yeah, I see we still have a few minutes. So
yeah,
let me ask another question to Thomas. So now this magic 20 GeV, somehow you said the compromise. Do we have hope to in some distant future, do we see the hydrodynamic calculation can go to really high baryon density? For example, at 500 MeV, or because we have data 3 GeV, we see clearly lots of indications. It looks like purely hadronic, but we don't know what to compare and how to extract the information. And you know what I mean? Because it looks like you say, okay, at the 20 GeV, we cannot go to higher baryon density, meaning lower collision energy anymore. So that's why we pick up.
No, yeah, I mean, I didn't quite say that. So this is I mean, it's of course always a question as to how far on the edge you're willing to live. And in some sense, it's somehow beyond my real expertise. So you should really ask somebody like Uli or like Chun how far down they're willing to go. I mean, ultimately, I think what needs to be done more is indeed somehow careful comparisons where we use either a pure hadronic transport and run it against a hybrid, or we run a hybrid and play around with the precise way in which we switch between a hydro phase and a hadronic phase. And we see what the uncertainties are as we go to lower and lower energy. Of course, there is no one, you know, there is no one place where hydro is valid above that and it's not valid below that. It's a somehow smooth transition where the uncertainties become bigger and bigger. And it's obviously a kind of quantitative question, just how far you can take it. And I don't think I'm quite the right person to ask.
All right, thank you.
Okay. Is there any other question for Thomas at this point? It doesn't seem to be the case. So Thomas, let me thank you again on behalf of all the organizers for this very nice overview, and see you all next week. Bye-bye.
Thank you, Thomas.
Bye.
Thank you. Thank you.
Thanks.